Okay, so I'm Shengding Sun from Georgia Tech, and this is joint work with my co-advisors, Greg Beckerman and Shantanu Day, and also Marco Molinaro. And we'll motivate this by consider the usual SDP, which we enforce the matrix X to be in the positive semi-definite column. So this is polynomial time, but it will be slow for large instances. So in other words, if n is large, it's very slow. So one possible way to remedy this is we only enforce the positive semi-definiteness on certain the principal submatrices. So in practice, I referenced two papers here, but what they do is for these two applications, they basically enforce this positive semi-definiteness only on the 2x2 principal submatrices. So in other words, you require this X to belong to some intersections of second order column. So we will generalize this by considering this new object S and K, which is defined to be the set of real matrices, the symmetric matrices where all K by K principal submatrices are positive semi-definite. We think this is a very natural object to consider if you want to generalize this like second order construction. So another way to say this is that it's the all symmetric matrices where the quadratic form is non-negative for all sparse vectors. So in particular, I think it's worth to mention that in the case where K goes to 2, the dual cone to Sn2 is exactly the set of scaled diagonally dominant matrices. And after we define this object, our main goal is to study how close this new Snk approximates the usual PSD column. So we use the metric defined as follows. So we will consider among all matrices in Snk, what is the farthest distance from this matrix to the positive semi-definite column. So we call this the normalized Frobenius distance. So in other words, among all matrices in Snk where the vector of eigenvalues have length 1, what is the most negative weight that you can get? So the weights of all of these negative eigenvalues in the L2 sense. And first, I will present some simple bounds. So suppose we have a matrix, so this is going to be an upper bound by averaging. So suppose we have a matrix in Snk, so that means all K by K principal submatrices are positive semi-definite. Then for any principal submatrix J, we can just keep the entries that in J and zero out everything else. And this matrix will by definition be positive semi-definite. And then we let A prime to be the averaging of all such AJ. And we can observe that you can just scale A1 by scaling the diagonal entries and off-diagonal entries by different weights. And then we can just scale this new A prime to get a bound for the for the upper bound for the normalized Frobenius distance. And this upper bound has another advantage, which is achieved by sampling. So if you have enough samples, then basically you can show that if you sample over all these minors, and I guess the advantage is that you don't even need to know that the matrix is positive semi-definite on all minors. Here, let's say you sample these many minors and you say if they're all positive semi-definite, then essentially the same bound applies like in a probabilistic sense. Because essentially if you average over these minors, it will be essentially the same as averaging over all minors if you take the sample to be large enough. And for the lower bound, we will construct specific matrices in Snk that are close to Sn. So we will consider the case where we scale the matrix where all diagonal entries are K minus 1 and all off-diagonal entries are minus 1. So if you see this matrix, all of its K by K principal submatrices are PSD, and it has only one negative eigenvalue, which is minus n plus K. And you need to scale this to have Frobenius norm 1, and then you get this lower bound for the normalized distance. And now if we compare the two upper bounds for the charts, then we see when K equals to 2, they match exactly the same. And in general, if K is a constant, then they also differ by a constant factor. But in general, there's a roughly square root n gap for both small k and large k. So small k in here means that it's a small fraction of k, of n. And large k means that it's close to n, and which will be C as well. So now we will use some more refined techniques to construct these matrices that we want. So for the small k case, we'll consider this is the restricted isometry property matrices, which are widely used in signal processing and electric engineering. So roughly speaking, a matrix is RP if it basically roughly approximately preserves the length for all sparse vectors. So it's K delta RP if for all K sparse vectors X, the length of AX is about the length of X by a factor of delta. And why is this useful for, I guess a very well-known result in the RP is that if you take a random matrix, whether Bernoulli or Gaussian, it's with the good probability it will be RP, and we will use the Bernoulli matrices after scaling. So why is RP useful for us? If you have a matrix A that's in M by N matrix that's K delta RP, then you do A transpose A minus the 1 minus delta times identity. You see from our definition, this matrix will be automatically in SNK. But furthermore, because A transpose A only has rank M, so you know this matrix is guaranteed to have n minus m copies of negative eigenvalues of at least this much. So there's some other calculation going around, but in the end, you can achieve this bound, which is for the lower bound on the normalized distance. So notice this bound is independent of n. And this actually matches our upper bound for the small k case up to constant. So you see, but the ratio needs to be very small. It's to be less than 1/93 for some technical reasons, because basically because of the strength that we quoted from various papers. And then for a large k, we consider this method of sparsification. So when k is close to n, then from interlacing theorem, we know there will not be many negative eigenvalues. So now we turn to the task of finding the most negative eigenvalue. So the idea is that, so let's say V is the eigenvector for the most negative eigenvalue. Then what we do is that we randomly choose a k sparse vector W in some fashion. So actually, I mean, the details are in the paper, but we don't have enough time to present everything here. But basically, you sparsify this vector V in some random fashion W. And because your k is close to n, you're not zeroing out many entries. And hopefully, your W will be close enough to A. But because W is k sparse, then you know W transpose the MW will be at least 0. But since W is close to V, then you get the upper bound on lambda using this way. And there's a bunch of calculations around, but in the end, you get this bound. For the lower bound, again, there are constants around. So for conclusion, I think this chart might be more visually useful. So here, the red bounds are what we get from the refined techniques by RAP and by random sparsification. And we see that in the case where k equals to a small ratio of n, then they match up by constant, which is dependent on R. And if k is close to n, then we see this bound, the previous factor was a root n factor, and now this is changed to a root n minus k factor. So this means if n minus k is kept at a constant, then these two, they also will match by a constant. So notice that there are still cases, for example, what if k is in the middle? And also in this case, the upper and lower bound are not sharp. So we will point out some current and future directions for research. So we should complete the, so I guess the first thing is to figure out what will happen for the remaining cases. And also, what about if we use some other measures for distance between the two cones? And I think maybe more interesting towards the practical sense, we probably do not want to force all n choose k minus principal submatrices to be positive semidefinite. So in this case, we will consider what if we force less submatrices to be PSD. And I guess a particularly interesting construction is where the case where each off-diagonal entry is covered by exactly the same number of submatrices. So these are known to be the two designs in combinatorics. And finally, it's more interesting to study more geometric properties for SNK, for example, the extreme rays. Okay, thank you.